Look at a storm front or a crowded city intersection, and the world appears messy. It feels like pure chaos. But we have to ask if there is a hidden rhythm dictating exactly how those clouds move or how those cars flow. Mathematics is the search for that rhythm. It is a creative effort to find patterns and, more importantly, to explain why those patterns exist in the first place. By identifying these recurring rules, we can begin to organize the noise of the world into something predictable. We can see this logic in the most basic sequence we have, the counting numbers: 1, 2, 3, 4. If we isolate the odd numbers and add them together, we find a curious result. 1 plus 3 equals 4. Add the next odd number, 5, and the sum is 9. Add 7, and we hit 16. 4, 9, 16. Each sum is a perfect square. No matter how far you extend this list of odd numbers, the result is always a square. The numbers show us that the pattern is real, but to understand why it happens, we have to translate these digits into shapes. Think of the number 1 as a single physical point. Add 3 new dots in an L shape to create a 2 by 2 square. 5 more dots expanded into a 3 by 3 square. The next odd number is exactly what's needed to build the next layer. Now consider a different sequence. What happens when we count up to a peak and then right back down? 1 plus 2 plus 3 plus 2 plus 1. We can visualize these numbers as vertical columns, forming a staircase that peaks in the center. If we move those outer columns into the gaps, the staircase collapses into a solid block. It is 9 dots again, a 3 by 3 square. We've used 2 different numerical paths to reach the same geometric conclusion. This works for other shapes too. We can arrange dots into equilateral triangles for the sequence 1, 3, 6, and 10. Certain numbers, like 36, are flexible. They can form a rigid square or a perfect triangle, depending on the role they play. If we build outward in rings, we get the hexagonal sequence 1, 7, 19, 37. Some rules are purely additive. In the Virahenka sequence, you add the previous 2 numbers to get the next. 1, 2, 3, 5, 8, 13. Patterns also exist in lines. If we take a segment and add a triangular speed bump to the center, we have a new rule. By applying that rule to every flat segment over and over, we create the Cox snowflake, a shape where the perimeter grows more intricate with every single iteration. By shifting a single rule of addition or geometry, math provides the instructions for building infinite variety. These patterns connect our abstract drawings to the physical universe. By tracking the numerical patterns in the motion of planets, astronomers developed the theory of gravitation. That understanding allowed us to calculate the trajectories required to send rockets to the Moon and Mars. We use those same orbital calculations today to maintain the satellite networks that power our global communications. In biology, the additive rules of the Virahenka sequence appear in the spiraling growth of sunflowers and pine cones. Identifying microscopic patterns in our genomes allows doctors to pinpoint and treat diseases by understanding the sequences within our DNA. Whether we are looking at a flower or a distant planet, mathematics provides the explanation for how these systems function. We apply these geometric rules to engineer massive structures, ensuring bridges can withstand the weight of travel. These principles allowed us to build the computers that manage modern economies and track the complexities of global trade. Take a moment to look at your own surroundings, your calendar, your watch, or the layout of your home. The patterns are already there, waiting to be described and understood. Learning to recognize these sequences changes how you see the world. Suddenly, you can see the logic connecting the smallest cell to the largest galaxy.